Okay, good. All right. Well, thank you for the invitation to give a talk here. So this is supposed to be focus week on three-dimensional black holes. The title of the paper I'm going to talk about and some work in progress is infrared realization of de Sitter 2 in AdS2. So there's no black hole there and there's no three dimensions there either. So to accommodate partially, let me change this to dsd plus 1, and then you can put d equals 2 there, and AdS2 cross S1, and I guess our theories have AdS3 and AdS2 cross S1 solutions. So maybe now it fits into the theme. So this work I want to talk about is work with Dionysios Aninos from the Institute for Advanced Study, and also some work in progress with him. I'll try to explain a bit what the nature of this work in progress is as we go along. So basically what I want to discuss is a bit, this is maybe a motivational talk. It's like an elevator pitch of maybe how we should think a bit about de Sitter in the context of holography. So let me start by maybe saying a bit why we care about some questions in de Sitter and why these questions are hard. So let me start with the drawing that everyone makes. So de Sitter. So let me draw the Penrose diagram. So something like this, like a square. And this is the end of time. It's called pi plus. And these two edges are the north and the south pole of the spatial spheres that foliate spatial slices. And we are here, sitting on the south pole of the sphere, looking at the universe around us. And this region here is called a static patch. Now, if we want to do holography, I guess the state of the art is what's called the DS-CFT correspondence, which is maybe an ill-defined set of rules of maybe how we should think about de Sitter in the context of holography. And what these rules say is, well, let's try to take some of the lessons we understood in AdS holography, and let's try to transport them to de Sitter. And what you want to do in this case is maybe rather obvious, which is that you like to find some asymptotic region like an AdS where you can put some boundary conditions and maybe try to ask some questions in a dual field theory. And then the obvious place to do that from under this dogma is here, it's at scribe plus. So the type of observables that you will consider here are like quantum field theory observables for a theory that lives at the end of time and some sphere at the end of time, and you will compute correlation functions of things of this sort at the end of time. Now you can call this point of view a meta observer point of view. It's a meta observer because as you can see, all this theory is Euclidean by nature. It's not just an artifact, it's really Euclidean by nature. This happens at the end of time. And then the observables that you would like to define here are spatially separated. So if we look at our universe and the fate of our universe, and you ask about these observables, it's not very clear who is making these measurements. This might be well-defined observables, not clear who has access to them. So I guess these are a bit better understood in the context of inflation, because then there's the initial de Sitter phase, and then you can measure correlations in this Euclidean theory that will have a signature in our current phase of the universe. And then this come in causal contact, and then we can say something about this. But at the end of time, it's a bit confusing how to think about this. But let me get to the bad things in a second. Let me start with the good features why we think about this. One reason we think about this is, as I said, because these are the natural place for boundary conditions. And people have tried to exploit this to define the wave function of the universe in the context of DS-CFT. And very importantly, and I think this is really what guides us, this is why we don't have much better ideas, is that this is a good place to define gauge invariant observables. So it's not clear who has access to them, but at least they're gauge invariant. We have a boundary. Gravity sort of decouples there to some extent. We can discuss to what extent that happens. But then we can define correlation functions in a CFT that are gauge the diff invariant. So this is a place where you could try to do these things. And I guess are good features. So let's put a smiley face next to them. So those are good things that, about this approach. But there's a series of things that you might worry about. So I guess the first thing is what I already mentioned, which is that the dual theory is Euclidean. And as I said, in this cosmological setup, it's very unclear what the meaning of that is. Why would we care about those observables? It's a bit unclear. Related to this is the fact that there are complex weights appearing in the dual of this theory, so compound weights. And whatever. And you know, the theories, even questions like reflection positivity are not clear. Questions about reflection positivity are not even clear. So example of this is, of course, this construction, this higher spin construction of SPN for this sort of approach, where questions like reflection positivity start bothering us. Well, you don't have to. But this is the whole point. We don't have to, and then we get confused because, okay, we understand theories that satisfy this more than the theories that do not. And then it's, again, unclear what the nature of observables are in a theory that's not the Euclidean version of unitarity. So the rules of the game are a bit more unclear. Maybe I'll have something to say about this complex weights in a minute. Okay, but it's related to this issue. It's not clear what time evolution means. So in AdS2, radial evolution has a very precise meaning as an RG flow in our CFT. Here it's a bit less clear what that means. In principle, that's a Lorentzian direction in the sitter. And okay, maybe it is related to some sort of RG flow, but it's, again, a bit unclear what that means. Maybe it's also related to the fact that the theories are a bit different, and maybe what the RG means in this case is a bit of a different thing. But you think it's inverse RG flow? Maybe. While that might be the case, it's well, maybe. This, of course, the issue that this theory lives at the. You think of the theory living at the boundary, and it's a bit unclear what it means that this inverse RG flow if you think of the theory living at the boundary, right? Because no, that's true. That's true. But what I'm saying is that here near scribe plus is where you have a very large number of degrees of freedom. So you would suspect that that's the the UV. Okay. So why? Okay. So it's not an inverse RG flow. You say. Well, in AdS2, well, okay. Whether it's a direction of time, that's a different issue. But the point is that that the UV theory lives at the boundary. You would say. And so in that sense, it's the same as AdS. Okay, it's because you're going to give a directionality to time. Okay, fine. No, I agree. Now I understand what you're saying. Very good. Then a very interesting question, which is related to other issues, is that, of course, there's a cosmological horizon in the sitter solutions that has a temperature associated to it. And, we learn to think about those horizons as doing some statistical field theory at a finite temperature. But it's a bit confusing, see, because now the theory lives inside the horizon. You don't have the type of interpretation that the horizon is shielding you from some, details of some state that you don't know, but you're actually putting the state that you're worried about inside the horizon. It's a bit like if you were doing black hole physics, you're trying to resolve the singularity of the black hole, to try to put a field theory where the singularity of the black hole is. It's a bit confusing what the meaning of the horizon is when the state that you're defining is really here. This seems to be more to do with microscopics and has very little to say, it seems, about the temperature of the horizon. Makes you wonder all of these features, whether maybe the CFT is not a microscopic theory, but maybe some average type theory that's, that knows something about the average over some landscape of solutions. A related question as well is that the central charge in this theory seems to compute the temperature more than anything else, more than counting degrees of freedom, which is also a bit unusual. So there's all these sort of issues about behind the horizon questions that are a bit confusing. So all of these things, I would say, do I have more complaints? Well, maybe not for now, but all of these things are maybe things that you might be a bit uneasy about. So a very important question, something that makes confusing all of this story, is that in the sitter, the temperature is fixed by the cosmological constant. So it's very different from AdS, where the local geometry has nothing to say about the temperature, and then you have a knob, which is a black hole that you put inside, and then you can move this knob and make it whatever you want it to be, and it's a global property. An observer has to measure some global property of the space-time to know what the temperature is. Here in the sitter, the temperature is more of a local property. It's set by the cosmological constant. You can just measure it locally, and then you cannot change it. It's frozen. So that's a bit complicated to understand. So cosmological constant and temperature are related, and it seems it seems like the theory is deciding its own temperature, and that's, again, from a quantum field theory perspective, very unusual. So one question that you can ask, and I guess this is where I'm going to go as fast as I can, is what quantum mechanical system does this? How do you achieve this feature? How does a quantum mechanical system select its own temperature? Well, at very late times, of course, you will recover the sitter. I know, and then you have to worry about the question of the temperature at the end of time. So there's always a late time phase where you have to worry about these questions. And if you take this point of view, you cannot escape this fact. But maybe I'll say something that goes along those facts. But within this paradigm, I don't think you can escape this problem, because this is at very late times. But maybe what I'll say now is along the lines of what you're suggesting. So okay. So maybe another paradigm that one would like to push, that maybe this is not the most natural place to ask questions. Maybe this is a more natural place to ask questions, to really just follow our observer that's free falling in some wall line, and this guy is asking questions here. Maybe we want to ask questions from this guy's point of view. Some of these issues will improve, but of course it's not it's not a paradise. So let me start maybe with some things that are a bit confusing. First thing that's confusing is that the symmetry group of the sitter is reduced. So the static patch of the sitter does not have this manifest full de Sitter geometry, but it has instead this geometry, this isometries, because the other ones take you outside the static patch. So by considering this theory, you're manifestly breaking the symmetry of the sitter. So that we can discuss whether we're worried about that or not. I guess more importantly, there are two related questions, which is how do we impose boundary conditions? So let me talk about this in a second. And also this issue of gauge invariance. So this issue, these two questions are related. And the problem here is that very much unlike AdS, the wall line of an observer is not decoupled from the rest of the geometry. It's at finite distance from the horizon. It's a place that fluctuates. It's allowed to fluctuate and interact with the fluctuations of the geometry. And it's not clear how you would put gauge invariant boundary conditions there, how you would even define gauge invariant observables. So this is, I guess, the main obstacle that makes people think more about this point of view, because it's a very confusing thing. On the other hand, so let's postpone this for a second, maybe like this. Let's postpone this for a second. But we are this guy. So if we want to ask questions ourselves, we might as well have to figure out how to do this physics. Okay, so I think an unavoidable question. There's good thing is this description is more black hole-like, in the sense that now, if you say you manage to understand what's going on here, then these questions of thermal field theory become relevant again, because now the temperature is something that's shielding, is preventing you to access a full knowledge of what the state is, and then we're back to more familiar AdS CFT type reasoning. So this connects to the AdS2 thermal point of view. Related to this, now the entropy might make sense. So can we get entropy from quantum mechanics, from quantum field theory? So it's the same question. Can we now interpret now this entropy as some information theoretic quantity for that particular observer? Now, something that's a feature, that I'm not sure you'll be happy or not, is this thing that I mentioned, that quantum gravity does not decouple. So this observer is not in there's no decoupling limit for this observer. So you have to live with quantum gravity for this guy. So the world line of this observer is fluctuating. And what that means is from the guy that just sits there and wants to define observables, he has to say this guy lives on a world line, he wants to define a quantum mechanics on his world line, he has to couple that quantum mechanics to 0 + 1 quantum gravity. There's no escaping that. That's not necessarily a bad thing. 0 + 1 quantum gravity is not infinitely difficult, so maybe we can do something about that. But this is a feature of this geometry. And this is not so bad news because this connects to this story. Because now, if we're now willing to sum over boundary conditions, over metrics, then we might have an idea of how to define these objects very precisely in a gauge invariant way. So quantum gravity just maybe provides you the way to define these observables. So it's not a bad thing. So this is very different from AdS2 from this point of view. Another good thing about this guy is that now you can think of the observer as introducing a defect. The observer itself is generating a defect in the geometry, and it back reacts because there's no decoupling limit. So this guy is really back reacting. And when you put a defect in the sitter, you can think of this. You can in principle put a black hole, say, in the sitter or a defect, doesn't matter. It will back react and it will change the size of the cosmological horizon, which is giving you a knob. So the knob here, so this gives you a knob for the temperature. So this will change the properties of the cosmological horizon. But the interesting thing here is that the observer itself, the existence of someone asking questions, is what introduces a knob for the temperature, which we did not have in empty de Sitter. Maybe related to this question, I should say that, say you believe that there's some quantum mechanical theory that describes this world line. Now, typically, we have reasons to believe. So in previous paper with Dionysios and with Sean Harnold, we studied this type of correlation functions in a very simple-minded setup within just solving wave equations in the Sitter space, and we found some conformal structures in this setup that they're hidden. They're not obvious symmetries of this geometry, but they are there. But what's interesting is that conformal quantum mechanics, as I will discuss briefly in a minute, they typically have vacua that break the conformal symmetry. So the fact that this happens is not fatal. It might even be a good feature that you observe the symmetry breaking, because conformal quantum mechanics typically have vacua that break the symmetry. And I will come back to this in a minute. So let me just say one last thing, maybe. Well, no, let me postpone this. So maybe I should pause here. So this is a bit the idea of why I want to motivate this thinking about this observer. And now I will tell you a bit the way in which we will get a handle on this guy. So any questions at this point? No. Very good. So very good. So now the question is, how can we understand this static patch quantum mechanics? And how can we get a handle on it? And maybe there's some work in progress where we try to understand a bit more these quantum gravity features. Let me just say one more thing. There's something that I have not mentioned here, that because there's no decoupling limit, the volume of the sitter is finite, which suggests that the degrees of freedom that make up whatever quantum mechanics responsible for the sitter is a finite dimensional quantum mechanics. And that's actually quite interesting because it matches quite well with this idea of having to couple with quantum gravity. Once you couple quantum mechanics to quantum gravity, you can think of this as a Wheeler-DeWitt constraint, and it will reduce quite dramatically the size of the Hilbert space, and typically would make it finite dimensional. But I guess I'll come back to that. Now, one could try to approach this problem directly, and I guess this work in progress that I mentioned relates a bit more with this idea. And if there's time at the end, I can tell you a bit what the ideas are. But say you want to avoid that question of quantum gravity, and then you want to say, what can we do without thinking too much about that problem? And then, in order to do that, you have to ask, what kind of quantum mechanics do I need? And the surprising answer to this question is that there are not too many options. Quantum mechanics is fundamentally different from quantum field theory in higher dimensions. And the main reason that it's fundamentally different is that the UV behavior is universal. I'll explain what this means in a second. So in quantum field theory, we're used to the idea that the quantum field theory is a very complicated beast in the UV. There's an infinite number of irrelevant deformations that can do very, violent things to our quantum field theory, even destroy it. And then there's just a few relevant and marginal deformations that takes us to some interesting fixed points. But the UV is completely non-universal. It could be anything. And that's a bit the power behind quantum field theory. Now, in quantum mechanics, the opposite happens. So in quantum mechanics, so just to take an example of scalar field, just to fix concepts. Scalar field, x. So the dimensions of x are -1/2. And what happens is that any regular potential B of x is a relevant deformation. This is very surprising. There's really very hard. It's very hard for you to find marginal or irrelevant deformations of quantum mechanics. It's very easy to change quantum mechanics in the IR, but it's very hard to do it in the UV. Sorry? Well, they will, of course, yes, no. You can, of course, worry about higher derivatives, and then we can talk about that question later. I'm mostly interested here in conformal theory, so I might worry about what those mean. So we can. It's an issue of how you preserve unitarity. So maybe I'll give you an example within the potential class of why I'm not worrying too much about the kinetic terms. But let's say take a canonical kinetic term. It's very hard to do it. And I don't know of a proof, but I suspect that most of the things you add with higher derivatives will destroy unitarity. I know, at least for the case of potentials, that this is the case. Yeah, many x dots. Sorry? 1? That's topological. Oh. Oh. No, you can have many other things. I agree, and people have built conformal systems that are rising. Sorry? I agree. I'll give you an example that's equivalent to that one up to field redefinitions in a second. So people have used these things to create multi-center black holes and get conformal quantum mechanics that have those type of terms. But let's get to that in a minute. Okay, good. So the reason why this happens, the reason behind universality, is really that quantum mechanics at very high energy always becomes WKB. And then the theory is just a theory of free plane waves. And then the theory is just free. So the theory wants to be UV free. So maybe I should go fast. I'm not doing so well on time, so let me try to go fast over the examples. And I'll come back to class as equivalent to the class of examples you just described. So first example is just quantum mechanics with an infinite Hilbert space. And as I said, the theory is UV free. And in holography, an example of this is BFSS. So there you see this happening, actually, that you have some theory of these zero brains, and then you look at the UV, and the theory becomes weakly coupled in the UV, and then, okay, generates flat space or something that we don't fully understand, that you have to go beyond supergravity to understand. But the theory becomes weakly coupled in the UV, and typically you get things like this type of models, if you want to understand that. No, I understand, but the UV fixed point is something, you might hope, and that I'm saying that the theory wants to become free in the UV. Another way of saying it is also related to the size of the Hilbert space, that the spheres, the S8s, are becoming very large, and the theory becomes weakly coupled. Now, I'm going to go a bit faster than I thought, because I do want to get to show you some other results. An example that's related to what you were saying is that, so what can we do to tweak this to actually make it strongly coupled? So I said that there's not many things you can do to the UV, but there's one thing you can do. So these potentials, turns out you can show that if you now allow singular potentials, then you can of course try to get closer to getting irrelevant deformations. But the result is that exactly when you would get irrelevant, the theories destroy, this potential destroy unitarity. The potential becomes so attractive that the particles fall to the center, and then the theory becomes non-unitary. And exactly the boundary case is a marginal deformation. So there is this conformal quantum mechanics. Given by something like that. And exactly this case is a marginal case. And if you have something more singular, it will not be unitary. But in this case, this theory is this is a marginal deformation that allows us, is one of the few nodes that we have, so we can move away from weak coupling. And some of the examples that you mentioned can be recast in this language by field definition. But they have the same features, that there's a marginal deformation that allow for strongly coupled UV fixed points. And yeah, so for this thing to be okay, G has to be greater than -1/4, and then the theory will be conformal, and then this is a marginal deformation. If G is less than, so you might worry about what happens with G goes less than this number, and when that happens, you can, in principle, at the cost of conformal invariance, you introduce now an RG flow, and then what you find that this guy actually is marginally relevant. So it does. You would think, right, that it's more attractive and then it wants to become irrelevant, but actually it does the opposite thing, and it becomes marginally relevant, and the theory is always free in the UV. So you can calculate the beta function, it's always free in the UV if you violate this bound. And what happens within holography, of course, that you expect to see AdS2 type geometries. Now, this is not exactly true because, as I mentioned very briefly, these theories break, the vacuum of the theory breaks conformal invariance. And because of that, then we don't expect AdS2 to arise as a vacuum, and maybe something else, maybe it's a sitter, maybe something else, but it's not AdS2. And a tweak on this theory is all this work on SYK, where the conformal invariance is not saved completely, but at least it's just very weakly broken by logarithmic runnings. But the physics is on this sort of universality class of physics, and this you move from flat space in BFSS to AdS2 by going to strong coupling. But there's not too many things you can do. Yeah, this is of that type. This is of that type. And let me do the maybe last example, and it's what happens if this is finite. If the Hilbert space is finite, sorry, okay. If the Hilbert space is finite, then see, by going to strong coupling here, you opened up sort of a AdS2 throat in the U. You open up this boundary. When you make this thing finite, so like the opposite happens, and the geometry wants to cap off, both in the IR and in the UV. One way of thinking of how this can happen, of course, is by quantum gravity. But the point is that something that has sort of these features is, of course, just now, let me write it now, is something, a metric like the sitter. So this is a question. This is, of course, we don't have good examples of this, but if you just write the sitter for the static patch, it looks like it has a bit this feature, right? Which is that say near r equals 1, you have the cosmological horizon, and the theory sort of stops running at that point. And near r equals 0, the sphere shrinks, and then there's no degrees of freedom, and then that's the statement that Hilbert space has to be finite. So we need to understand a bit this example. We want to get a handle on these examples. And the way to do it, the way we will do it, so let me just, I don't want to bore you with details. I'll just show you what the setup is, and maybe give you some features of the setup. Is that one way to get a handle on this is to try to, and to remove this quantum gravity feature, is to try to glue this sort of behavior at the IR of something that we maybe understand a bit more, which is more of this kind. So we're removing this quantum gravity type destruction of the Hilbert space by some completion that we understand, and we hope that we can then understand correlation functions within more classical AdS setup. So the idea is the following: take AdS2, global AdS2, which in Euclidean looks like something like this, has two boundaries. That's global AdS2. And the idea is to replace this by something we call a centaur geometry. Centaur's geometry, which is where you just change the theory in such that one of the sides collapses. and then one of the boundary disappears, and then this thing cups off. Sorry. So something like this. And then this thing is cupping off, and there's a sphere at the tip, and then this part of the geometry is removed. Okay? And then the geometry would be de Sitter in the far infrared and AdS2 in the UV. Now, what theories do this? How can you engineer this type of things, and how do they fit with this paradigm that I was trying to push? So let me just... What, sorry? The name. It's like a centaur. See, it's like a horse, human. So we are the sitter, we are the human part. AdS is a horse, it's a centaur. Okay. So what theories have these solutions? So I want to show you that it's quite generic, given certain mild assumptions, and I want to show you what's the physics that arise for these cases. So one way to get these solutions rather easily is to consider some dilatonic gravity models that are very similar to what people do for SYK. So let me just write an example. So something like this. There's a part of the dilaton, something like this. And this sign is important. I'll talk about it in a minute. And this is the AdS scale. So this is a theory. Now the full dilaton is given by this minus that. So this is a constant part, and then there's a part that can fluctuate. And I was saying that this sign is very important because this sign is the opposite of what you use in SYK. And what this sign is saying is that you're fixing this constant part to a very large value. This part will, again, maybe for the experts, this part determines the very large degeneracy of states associated to AdS2, to the vacuum of AdS2, but it's very rigid. You cannot do much with it. It's just a very large degeneracy of the vacuum. And then this is moving away from it, and as long as this phi is not very, very large, then you have control over this. If when this number of this order, then the theory becomes strongly controlled in the back, and then you lose control. So what's interesting is that in the SYK models, the dilatons that the dilaton models that you write typically have the singularity behind the horizon, say, in the far IR, but these models have the singularity in the UV. So this is quite interesting because see, from the dual quantum mechanics point of view, what this is signaling is that the theory wants to become weakly coupled in the UV, like the universal quantum mechanics that I was describing. And we can do holography as long as we put a cutoff just before that happens, and then we can do holography there within this strongly coupled region and get an AdS2 UV boundary. So let me show you a bit that these solutions exist. So so the equation of motion that comes like this. The energy momentum tensor of the dilaton has to be 0, and that R plus L square B prime phi equals 0. So they're very simple. And this shows you exactly what you need to do. You just need to have a potential that interpolates between a positive constant to a negative constant. And if that happens, whatever happens inside, basically, satisfies some monotonicity in things that you want, such as the theory is not pathological. But up to that, then as long as that happens, then this theory has solutions that interpolate between AdS and the sitter. The solution to this theory is very easy as well. You can use the dilaton to parameterize a coordinate, and then you can write the metric in the following manner. Where this function n of phi is given by some integral from some horizon. This is just some integration constant, some horizon, to whatever phi that you want. So now phi lives in phi h, and say infinity. This is really the boundary. You have to regularize this, but it's a boundary. And as long as the potential looks like 2 to get the standard normalizations, as phi larger than some scale that we'll discuss in a minute, and phi much the same scale, As long as this is happening, then the theory will have, for very large phi, an AdS solution, and for very negative phi, a de Sitter solution. This epsilon is just some IR scale that's just parameterizing the interpolating region that we don't know. So basically, this potential just looks like this. So here goes like phi, here goes like minus phi, and here some size epsilon is where it interpolates. That's what the potential looks like. And as long as that happens, then you can have solutions that interpolate between AdS and de Sitter. Now, so this is the part that I don't want to bore you with details. I'll just give you the results, also in the interest of time, I guess. Say that again? Well, that's up for you to decide, but in this particular case, we just pick it symmetric, and it's the same size as AdS, so the curvature is the same. Well, maybe what you're asking is the following. So it's connected to the temperature, right? So now there's a phi h, which is the temperature. So maybe let me mention this now. So say you pick a temperature here. So see, if you have an AdS2 solution, the temperature means nothing, because you can pick any and they're all the same. As long as it's non-serious, they're all the same. This geometry is different. This geometry does have a temperature. That's meaningful. That means something. Why did this happen? It happened because there's this epsilon scale, and maybe this is what you're asking. There's the size of this interpolating region that sets a scale. And then depending on how you compare the temperature with that infrared scale, then you can change the size of the cosmological horizon. That also is quite interesting, because you can interpret the size of this interpolating scale as the size of the defect that lives inside the de Sitter. So I mentioned at the beginning that you can introduce a nov in the de Sitter if you just think of the observer like a defect. And in that case, epsilon, you can think of the de Sitter with an AdS2 defect inside, and that thing back reacts, changes the size of the horizon, and then that's determined by the ratio of phi h to epsilon, which is now a physical parameter. So this theory does have a temperature. So in that sense, it's different from AdS2. So let me just give you some features about it, and then I'll try to wrap up. Okay? What's that? The two me is just conventions. It's just, it can have different slopes. Yes, that's what I'm saying. I picked it symmetric, but it can have different slopes. Yes. So you can calculate things like the temperature. So you just solve for this thing, and then you look for the to regular. So the temperature is to the value of the potential at the horizon. So see, it's very easy to get the formula. It's for any potential, you can just get this formula, and it's phi h goes to minus infinity. So if it's very large, then it's just 2 pi over L phi h. So as you can see, this integration constant is just selecting the temperature of this solution. If the temperature is very close to 0, then these solutions, what they look like this. They look like AdS2 throats, and here the geometry becomes flat. And so you can think of this limit as a decoupling limit between the two sides of the AdS2 two-sided geometry. And in this limit, you're just making the bridge very, very, very long. There's no time like this is Euclidean time. Sorry? No, you can Lorentz, you can weak rotate this. These are good solutions. There's nothing pathological about them. No, because you don't. This geometry doesn't have time-like loops.
Maybe we can carry on in the discussion. Just let Diego carry on.
Yeah. So let me finish. I'm almost done. So interestingly, you can also calculate the specific heat in the theory, and it also has some very nice formula, just given in terms of horizon data. So now let me make a point here. So what's interesting about this specific heat is that it is positive for the de Sitter solution. This theory also have AdS2 solution. So see, for a given temperature, which is just an absolute value of phi h, there are actually two solutions you can pick. One that's here, integrating from here all the way to infinity, and the other one is integrating from here all the way to infinity. Typically what happens when you pick the other sign for the dilaton is that always the AdS2 solution wins. But with design of the dilaton, it's the opposite one that wins. It's always the de Sitter solution that wins. This one's the one that has the one's stable and has a positive specific heat. So the de Sitter solution actually beats the AdS2 solution. It's a dominating saddle in the path integral. And you can calculate more things. You can calculate the entropy, which is also finite. It's just this large constant piece, but that's something that depends on the temperature. And this solution is well behaved. So maybe since people, I'm running out of time, let me mention a few features and then I'll stop. So first thing I should say is that there have been previous attempts in embedding the Sitter inside AdS, and they fail because you violate some null energy condition typically. Now the reason that happens is because you're trying to embed ds d+1 in AdS d+1. And one thing you can do is you can just, one fast way to see there's something wrong is you can track the size of the spheres, of the celestial spheres in this geometry. And what happens is that near the boundary in AdS2, the celestial field is very large. As you approach the boundary of AdS, the sphere becomes very, very large. But as you, so this is AdS, but as you approach the cosmological horizon, it also becomes large. And then this non-monotonic behavior is signaling that there's some problem with the null energy condition. So you can translate this to a problem in the null energy condition. When you embed the Sitter, this example is two-dimensional, but there's nothing stopping you from pushing this to higher dimensions. And then you embed the Sitter d+1 in AdS2 cross a sphere. And when you do that, this changes, and it becomes monotonic. And then you can ask what it means that the sphere is getting large, and if I had more time, maybe I would say more things about that, but at least you remove this feature. Another way of saying is that the dilaton theory here has just a vanishing energy momentum tensor, and nothing can violate the null energy condition. The last thing I'll say, I guess, maybe I was planning, well, maybe I can still make a plot. So you can calculate quasi-normal modes and properties of waves in this geometry. So let me just make a plot. I didn't get to discuss this much, but let me just make a plot. If you just put some waves on top of this geometry, you calculate the quasi-normal modes, you will see a spectrum that looks like this. Now to compare, yeah. So to compare, this would be the AdS2 black hole. This would be global AdS. And this would be the Sitter. So what's going on here is that the geometry develops quite an interesting behavior. On the one hand, you have these dissipative modes, but as you can see, they're more stable, they're more real than certainly that the AdS2 modes and even the DS modes. This difference is not too large; it's a logarithmic difference, so it's not a big deal. But it's much more stable than AdS. And it's quite interesting because it's like in the Sitter, things have a harder time dissipating. It's not unlike what happens when you have charge degrees of freedom in a charged black hole. And again, there's some interesting analogy there that we can discuss. At the same time, there's some quasi-particle type states. These are states that live near AdS2 boundary. And because the Sitter throat is so small, they have a very hard time finding the throat. And okay, I guess my colleague, my partner in crime, likes to think about that as classy physics, as some degrees of freedom that have really hard time, have to really probe a lot of phase space until they find a throat and they can thermalize. But I'm saying that from the point of view of this deconfined phase, this is a quite different state from the AdS2 black hole. It's completely different physics in many ways, which again, if I had more time, I could explain in detail. But the physics is quite different. We need to think a bit again about what it means to think about thermalizing and the confinement in these geometries. Maybe to conclude, I would like to say that well, this story can be done in higher dimensions, so there's no obstacle to that. Of course, one would like now that we understand a bit what the rules of the game are, to completely remove the AdS2 throat and then just do the Sitter. I should say that these quasi-normal modes at very large n, so very near the end, they match, of course, what you would expect from the Sitter, and they match our previous results with Sean Harnell a few years ago about the correlation functions of the observer just in the Sitter. But basically what you like to do is you would like to UV complete the Sitter theory with something else that's not an AdS2 boundary, by just introducing some quantum gravity. And that's actually not unreasonable. It's very much related to the fact that the sitter has a fixed temperature. The temperature is not up for you to decide, but it's dynamically selected. And the reason it happens is that once you couple the quantum mechanics to quantum gravity, there's a competition. The theory wants to be at, to be a dominating saddle, wants to be at low temperatures, because now you have to sum over temperatures, right, which is the size of the Euclidean circle. So the temperature is not fixed anymore, like you expect in the sitter, but it's a dynamical thing that's selected. Now, the quantum field theory wants to have a very low temperature, because the free energy grows with the temperature. But as the temperature becomes very, very small, then the size of the Euclidean circle becomes large, and there are quantum anomalies that arise and give an energy contribution coming from that, from doing the path integral in quantum gravity. And these two effects sort of cancel, and they give you a preferred temperature. And what's interesting is that if you look at large n quantum mechanics, typically this temperature is suppressed by some power of n, depending on the theory. So depending if it's a vector model or a matrix model, they will be suppressed by different powers. But suppressed power of n, which is a bit what we see, that the sitter wants to have a very low temperature. There's some issues with this thing. This is not done. This is work in progress. But okay, this is a bit where you could see the story going. And before I kicked out of here, let me just say thank you.
Thank you. Yep. So, yeah. What happened with the two ends?
Yeah, good. So this is what I was saying. So it's the opposite of the SYK type setup. So inside it's completely healthy, nothing bad happens, it's all okay. But near the boundary, it blows up. But blows up means that
So
the effective Newton
so it's
constant.
not constant. It's not constant at either ends.
It's not constant at either.
So then you don't have really the sitter. You don't have the sitter isometries.
No, we do, because see, phi is, so this is why we selected constant phi. So high enough epsilon, this potential is as close, as linear in phi as you want, and then it really becomes flat. So it's really the sitter.
So it becomes a constant.
It becomes, well, it depends. It's an issue of an expansion in epsilon, yes. But to leading order in the expansion in epsilon, it becomes a constant. So for temperatures much larger than this epsilon scale, it becomes a constant. At low temperatures, it doesn't. So for example, I just gave you the example that at very low temperatures, it becomes flat. But at high enough temperatures, it becomes more and more like the sitter.
What about the other end?
What other? The boundary.
The AdS2 side.
Good. So at the boundary, this is what I said, that at some point, then you have to stop. The same thing happens. It becomes more and more AdS2, because this is linear, and it can be as linear as you want it to be. So at distances from the middle of the geometry that are much larger than epsilon, it just becomes AdS. In an epsilon expansion, it's really just AdS2. But of course, at some point, you have to put a cutoff, because otherwise the theory just goes into strong coupling in the gravitational regime. And you cannot trust the gravitational regime anymore. You have to put a cutoff, which is signaling that the quantum mechanics wants to become weakly coupled.
Perhaps one last question. Otherwise, let's Diego again.
So